Well, good morning to everyone. My name is Marja Braga. I'm from the International Relations Office at UFPR, and I would like to welcome you all to this panel session of the CU conference. Today, we discuss about the SDG 7, Affordable and Clean Energy. It is a pleasure to introduce the chairperson for this panel, Professor Luis Pereira Ramos, Senior Professor at the Graduate Courses in Chemistry and Chemical Engineering at UFPR. Dr. Ramos retired as full professor in Analytical Organic Chemistry at the Department of Chemistry of UFPR after 35 years teaching chromatography, spectrometry, and chemistry of renewable resources. He holds a PhD degree from the Ottawa-Carleton Institute of Biology, University of Ottawa, Canada, and is the leader of many research activities in the areas of renewable resources and biofuels, with a Scopus age factor of 42 for a total of 170 indexed publications, 23 book chapters, 3 edited books, and 17 patent claims. Also, he's one of the associate editors of the ACS journal Energy and Fuels since 2012. Participates in the editorial advisory board of the journals Bioresources and Frontiers in Bioengineering and Biotechnology, and has acted as ad hoc consultant for several companies leading international science journals and both national and international funding agencies. Member of the board of directors of US company named Earth Renewable Technologies, Dr. Ramos was cited by the University of Stanford as one of 100,000 most influencing researchers in the world based on the total bibliographic citations in 2019 and throughout one's entire career. Only 600 Brazilian scientists have been included in this list. Please welcome Professor Luis Pereira Ramos. Professor, the floor is yours. Nice presentation to all.
Thank you very much, Marja, for the introduction. I'd like to share my screen with you just for a brief introduction of some aspects related to our session. Can you see my screen? Okay, good. So again, thank you very much, Marja, for the introduction, and welcome everybody for section number 2 of SDG 7 regarding biofuels. I prepared a very brief introduction, and the first aspect I'd like to bring to you today is that you see, I've been working in this area of biofuels and bio-based materials for more than 30 years. And when I was still in the beginning of my career, I used to have a graph indicating that more than 80% of the global energy demand was supplied by fossil fuels. And based on the numbers that you see in the screen right now, things look pretty much the same, regardless of all efforts done so far by many. Of course, due to this choice in time, we are now facing the detrimental effects of this widespread and uncontrolled usage of fossil fuels, particularly for transportation. And this is not only for its environmental damage, but also for its tremendous impact on the economy of the developing and developed countries. So Brazil is not doing badly in that regard, both in the electricity metrics and also in the energy metrics. Brazil has very favorable numbers, sometimes close to the goals set up by ONU for 2050. But still, most of our renewable energy matrix is based on hydroelectric power. And now that we are facing a major drought in the country, it is clear that other things that must be done. We also have very successful biofuel programs, for instance, in biodiesel and ethanol, and those have ensured very favorable numbers for the country that are recognized worldwide. However, the new goals that have been established in the Paris 2015 meeting for the climate change conference set forth new challenges for the country. And that is to seek for an increase in the participation of biofuels in our matrix, as well as the exploitment of other biofuels, such as second generation ethanol, green diesel, dimethyl ether, hydrogenated vegetable oils and fatty acids, biohydrogen, biomethane, sustainable aviation fuels, and others. And more, after this last conference in Glasgow, new very important goals were established, basically to raise the participation of renewable energy to 50%. And for that, new biofuel programs have been launched, and these are related to hydrogen, biokerosene, and also CO2 reduction by aviation. It is important to recognize that biofuels themselves do not do the trick. You know, the concept of sustainable development is based on also products derived from biomass that have added value. And this, together with bioenergy in terms of bioelectricity, for instance, provide the pillars for sustainable development based on a circular economy. And biorefineries are very important in that regard because they provide not only biofuels for like the gross volume of product produced, but also small or smaller production of chemicals and platform materials, bio-based products that have a higher value and improve, therefore, the economic possibilities thereof. So in terms of biorefinery, we have like first generation, second generation, third generation, and fourth generation feedstocks to be exploited, and an array of different processes that are used for converting those feedstocks, mostly biomass, into fuels and chemicals. And for that, our session was established trying to tackle different areas within the concept of introducing more and more these biofuels into our economies. And yesterday we heard about biohydrogen by Professor Satinder Brar, and also aspects of synthetic fuels coming from CO2 conversion in the speech of Professor Claudio Motta. Today we have 5 speakers to tackle other areas, starting by Professor Martin Mittelbach, which I like to present right now as one of our keynote speakers. So having said so, I'd like now to interrupt my shared screen and introduce Professor Martin Mittelbach's background. So Professor Mittelbach graduated in chemistry and obtained his PhD in organic chemistry at the University of Graz, Austria. He retired from his lecturing activities in 2019 after more than 30 years of dedication to the Institute of Chemistry, where he was the head of the working group entitled Chemistry and Technology of Renewable Resources. Later, Dr. Mittelbach became the dean of the twin faculty for natural sciences from the universities of Graz and technology of Graz, 2 universities that were combined into this twin faculty named Navi Graz. And this was from 2009 to 2015. He's still active as a lecturer and consultant, as well as a member of different scientific organizations and specification committees, having 130 scientific publications in international peer-reviewed journals, as well as 3 edited and very important scientific books, several book contributions, 4 patents on synthetic organic chemistry, and over 10 patents on biodiesel production technologies, some of them very important for the development of this field. He was also the recipient of 2 scientific awards, the Energy Globe Styria Award in 2005 and the European Lipid Technology Award from the European Federation of Science and Technology of Lipids in 2015. So with this, I'd like to welcome Professor Martin Mittelbach for his speech. Martin, the floor is yours. It is a pleasure to have you here and an honor to hear you in this conference to address the question of renewable diesel or green diesel or other synthetic fuels coming from biomass. Please share your screen, open up your camera, and go ahead. Thank you. You have 30 minutes for your talk.
Okay, thank you very much, Louis, for the kind introduction. Good morning, everybody. I'm here in Graz. In the background, you see the mountains, how they look today, because winter started and we got the first snow. It's really a pleasure for me to join this conference. I remember the last time when I was in Brazil, it was 2019, just before pandemic started. So it was the last chance to visit different countries. I always enjoyed staying in Brazil. We had a very nice time there, several weeks on conference and also lecturing at the university. So we had, with Louis, I know him for almost the same time as he started working, as we started similar time very early on biofuels, and we had a chance to meet him and discuss a lot of things during these almost 30 years. So I will start now and with my presentation. Actually, it was the topic is just diesel fuels from vegetable oils, because Luis Ramos will speak about second generation later on. I will speak about diesel fuels general from vegetables. They are still very important today, but I also will show you the future topics and the situation, special situation in Europe. So I checked to the connection with SDG. So we had a session about SDG 7, but also, of course, it will cover SDG 13, 12, and 9, because it's a topic which is actually interdisciplinary and covering a lot of fields. So I will speak about diesel fuel. So maybe you will think, what about diesel? Is it the engine of the future? And we had this situation in 2015 where there was an announcement of these scandal started with Volkswagen, the biggest European car producer, where they had a lot of not problems, but cheating about these emission treatment, and finally they had to pay a lot of fines during that time, because the emissions, when the true emissions, they were big higher, and therefore there was a question: is it the end of the road for diesel? And what you see here, that Volkswagen announced that they will stop diesel engine production in 2035. But it could be happen as earlier. And all the engine manufacturers in Europe say, well, we want to stop the combustion engines. But is it really true? I don't believe that 2035 they will stop, but they have to change, because we have strict regulations in Europe about the average emissions of CO2, and therefore only with electricity the engine producers can reach it, because the emissions of an electric car are zero. They say it's zero. Of course, it's not zero, but they could be counted as zero. So it's not the end, I would say, for sure, especially if you look to transportation fuels. Transportation in aviation, marine, heavy duty, rail, and light duty road vehicles, you see this is a pyramid. So we have, of course, the possibility to change the engines in light duty road vehicles and urban services. Here, electric cars will be the future for sure, because there are no emissions, no local emissions, of course. But if you go to rail, well, we have electricity in rails, but still have a lot of diesel-powered rail systems. And if you go to heavy-duty road vehicles, there is no possibility to change to electric cars. Here you see it's going up from need for liquid fuels. So if we go up to the pyramid, we need the liquid fuels, and for electrification, you can, of course, start with this light duty. So for heavy duty road vehicles, transport on the road, and this transport is still rising in marine sector, and especially in aviation, there is a need for liquid fuels because of these high density fuels, and therefore also biofuels will play an important basis. We can not substitute the whole fuel demand by biofuels, but I will show you what's the total amount today and what will be the future. So just one slide of chemistry, because if I want to speak about biodiesel, I have to speak about what's biodiesel and what is HVO, HEFA, which already Louis mentioned. These are two diesel fuels, biodiesel fuels, which are produced out of vegetable oils or any similar microbial oils. It could be a lot of other, but it should be a so-called dry acylglycerol or that dry glycerin. The main difference is that for biodiesel, you have the reaction with methanol, you produce the fatty acid methyl ester and glycerol. With HVO, you don't need methanol. Methanol is also coming from normally from fossil sources, but you use hydrogen. You hydrogenate the whole molecule, put out oxygen, you replace oxygen by hydrogen, and you get a so-called paraffinic fuel and propane out of glycerol. And if you make a hydroisomization, you get branched hydrocarbons, which perfectly fit into or could perfectly substitute fossil fuels. They are called hydrotreated vegetable oils or hydroprocessed esters and fatty acids. A little bit complicated, but it's also called, especially in the US, so-called renewable diesel. So it's the same feedstock, and this feedstock is limited. And I just give you a short overview about the differences. Feedstock is actually the same. Triglycerides or any fatty acids or used cooking oil and so on. Microbial oil conversion on one side is a reaction with methanol and the other reaction with hydrogen. You could ask where the hydrogen comes from, mostly also from natural gas today, but maybe in the future out of water. Reaction conditions are for FAME quite moderate, for HVO in at high temperature pressure. The plant scale, it's very interesting. For farming, you can use any kind of scale. You could start with very small plants, but for HVO, you need industrial plants because you need a high sophisticated infrastructure. The yield is almost the same, I would say. Side products is glycerol, and on the other side, propane and some decomposition products. So the total yield is lower than for producing FAME. Production costs are higher with HVO, about, nobody knows exactly the data, but I would say 10–20% more expensive than FAME. And the fuel properties are for FAME very restricted, mostly the same properties for HVO you couldn't change. It's flexible. So you could use it also for aviation fuels, which is quite interesting. Therefore, HVO is favored as a possible sustainable aviation fuel in the future. The main difference, as I told you, that the glycerol is produced, and you should not forget that glycerol is a very, very valuable side or byproduct by biodiesel, and a lot of applications which I don't want to go into detail here, but it's valuable. It's more valuable just like instead of propane, you can just heat it, but here you have a chemical building block. So what's the global situation now? I think you see this also. In 2021, in 2020, we had a drop, a small drop. 21, it's still going up. We have a world biodiesel production, something about 40 million tons. HVO production is 8 million tons. So, and bioethanol, of course, it's the most prominent biofuel. It's 80 million tons. So the total global worldwide biofuel production is about 130 million tons. If you look to global demand for transport fuel, it's just the estimation. So there are different figures found in it. So we can estimate that we have something like 5% share of biofuels in the transport fuel today. So it will not be increased dramatically, but 5% is quite a good number. Maybe we could increase it in the future, 7%, 8%. So I have the problem, it doesn't work anymore. Yeah. So you see an estimation about this biofuel production. You see here, the major part is coming from ethanol. Then we have biodiesel and we have HVO. A small number of HVO. In 2020, we had a little bit decrease, and now 21, 22, 25, it will increase again, but HVO will increase more than maybe biodiesel because of this aviation fuel. Who are the major countries or regions? European Union covering about 30%, US 19%, Brazil 13%, Indonesia mainly producing from palm oil, Argentina, and rest of world. So these are these 1, 2, 3, 5 regions are the most prominent biodiesel producers. Here it's a little bit more detailed. I have to go up here. You see the numbers. I don't want to go into detail, but you see it's an increase, but not in Europe. We have almost reached a limit. It's just the production, not the consummation. Maybe consummation is even higher. We have to import also from Europe a lot of biodiesel from other countries, and also from Argentina, from Indonesia, Brazil. And you see that's this number. And here you see the numbers for HVO. HVO is increasing, so it's still going up, and the sum is something like 44 million tons. What are the feedstocks for biodiesel production? You see numbers from 2017 and now 2017 and 2019. The feedstock major coming from palm oil today, and it was still increasing, even increasing from 17 to 19. But this will change, I would think, especially in Europe. In Europe, palm oil will be banned from biodiesel production because of these environmental problems on palm oil production, and this will change. But that's the global figures, and maybe palm oil is used in other areas worldwide. Then on second is soybean oil, of course, and rapeseed oil. And third, rapeseed oil is a major source in Europe. Here you see the vegetable oil production, the total global vegetable oil production is not The biodiesel is just and you see it's in 2021 214 million tons, out of which 44 million tons are used for biodiesel. The total production is increasing. Why? Because the population grows, and the major is still palm oil. Palm oil is the cheapest one with the highest yield per hectare, and therefore it's kind of sustainable if you grow it properly. Soybean oil on second, and then we have rapeseed and sunflower. What's very important and not so really known in Europe, that most oilseeds are used for animal feed. So here you see total oilseed consumption, and you see that the major amount is used for feed, for animal feed. Of course, significant part, especially the oil, is used as food, and for industrial products is about 56 million tons, and out of which biodiesel is something like 50% of this industrial use. So the major feed. And if you want to, in Europe, we have the discussion to reduce the biodiesel production in Europe. Why? Because we have limited areas. If we reduce our areas in rapeseed oil, of course, we have to import a lot of animal feed, especially soybean meal, which is used for our animal feed. And that's not so well known in Europe. Here you see soybean, the major part is going to the meal, and it's just a smaller amount is the oil. In rapeseed, it's something like 1:1, and also for sunflower. So you can see in soybean oil, the oil
Martin,
is, yes?
Martin, sorry to interrupt. For some reason, your slides are not moving. You're still in global biodiesel and HVO production. Okay.
That's a pity. You should, so it's a global, this one?
Maybe,
oh, no, you don't see it? Okay.
No, so
okay.
Why don't
so you have to interrupt me immediately because.
Yes. And
yes, now it goes.
Move it now, please, to the next. Can you try to? Yes, it's working now. So
it works. Oh, you have to interrupt me immediately. Otherwise,
yeah, I have to wait until the next slide to make sure that. Anyway,
okay, now it works. I also had a problem with my computer to change it, and now, but if it doesn't work, please interrupt me. So here again, the biofuel production, which is rising, especially from 2020. And the major part is, of course, ethanol, and we have biodiesel and HVO. These are the main areas again, major Europe, US, Brazil, Indonesia. Here again, the figures, which I don't want to go into detail again, so I've told you already. And here are the feedstocks dominating palm oil because the cheapest oil and the highest production per hectare. It could be done, as I told you, sustainably, but in Europe, I think we will ban it in the future. Do we see it now, the change? Luis? Luis, do you hear me?
Yes, I do. Sorry. Go ahead.
Yeah. Okay. Here again, the vegetable oil production, and here the numbers that I told you that most oilseeds are used for animal feed, and only a small part, or it's something like 20% of the oil or 10% from the total seeds are used today for industrial, or especially the major part for biodiesel. Here you see the difference between feed and oil. It's a soybean totally different than rapeseed, and therefore the major output from soybean production is the animal feed, and the oil is something like a, well, byproduct, valuable byproduct. We have a lot of non-food feedstocks which were discussed in the past, but didn't realize quite a lot. So like chatrofa or camelina, mustard, castor oil, and so on. but it's only a small part. The major feedstocks are the feedstocks which I mentioned. These are the so-called first generation food based feedstocks and not these other varieties. But also advanced feedstocks are discussed, microorganisms. We have a lecture later on microorganisms, algae, and so on. They are far too expensive until today, so there is no significant amount from this. And also glycerol could be used maybe as fuel in the future. What makes a biofuel advanced? So also Luis will speak later on the so-called second generation, which means that they have a better environmental benefit. It doesn't need large areas from byproducts and so on. And these are, well, additional fuels which can be produced from this. One very important alternative feedstock is the used cooking oil, and they give you some figures for Europe, 27 countries. You see the maximum potential. It was a calculation which I have done for used cooking oil, collectible amounts, and waste animal fat. In total, you see it's about 10 million tons, and that's about the maximum substitution is 2.5%. So the challenge is the high price for used fats, because the used fats have almost now the same price like unused oils. It's ridiculous because a lot of biodiesel producers in Europe want to use cooking oil, and therefore a lot of oil is imported from China. It's totally ridiculous because normally they don't have any spent oil there. But anyway, and therefore Europe, the European Commission said they will make a cap in the European legislation by 1.7% from this used cooking oil. But it's a big challenge. So used cooking oil is not only coming from frying. What you see here, or most of the oil which is used for frying at households goes down the drain, and then it goes into the sewage system. And we had in 2017 a big problem in London, maybe you've heard about it, that a fatberg was discovered in London sewer and the sewage systems, which blocked the total system. It's at about amounts of 100 tons, and it costs quite a lot of money to remove it, and finally to make biodiesel out of it by Argent Energy, which is the biggest biodiesel producer in Great Britain. And also animal fat, which is not considered anymore for animal feed, so waste animal fat. Because of this BSE crisis, we have different categories, especially this specified risk material is a very hazardous problem. And normally, nobody 10 years ago, didn't know exactly what to do with that. This risk material, it contains also a lot of fat, what to do with it. And in a company where I, PDI Energy, we have cooperation since a long time, over 20 years with them, that developed a process, a so-called rep-cupped process, which could produce biodiesel from any kind of especially waste material. It's a high pressure, not the traditional reaction conditions. It's a high pressure reaction, 200 degrees, 70 bar, continuous process with also a catalyst and oxide, which could be reused again, and finally the products were distilled and they produce FEMI and distilled glycerin. And it was the question if this process could destroy possible prions and could be used for the processing of this specified risk material. And in April 2021, the European Food Safety Authorities evaluated this process and found finally that this process is equivalent to the processing method laid down for the former legislation, and therefore it could be used. And if you see that there are several plants using this technology not all of them the newest technology, but they are using these animal fats and use cooking oil. And you see Argent Energy in Great Britain, in Amsterdam, it's the biggest plant for producing biodiesel from waste cooking oil. And the newest one is in Cargill in Belgium, in the port of Ghent, where it will be opened 2021. There they are using this wrap cut process, and the capacity is about 115 million tons, 115,000 tons per year, different kinds of waste material. What about situation in Europe about legislation? It's quite complicated. Nobody really knows exactly what's going on. We had this Renewable Energy Directive 1, valid until 2020, and we are starting now the new RED, which still is in discussion. That's you see that total energy from renewables should come up from 20% to 32% for total energy, not only transport energy, total energy. In transport fuels, it should rise from 10% to 14%, including electric cars. And because of these, electric cars are really, well, developing very fast. Maybe this is under revision, that biofuel content will go up in the future. What are the key points? Minimum 14% renewable fuels until 2030. Advanced biofuels, minimum of 3.5. Each country of these 27 European countries should reach it. From 2021, the greenhouse gas savings should be over 70%, but there will be a cap for fuels out of food crops, the so-called first generation biofuel, maximum 7%, and from waste and oil, maximum 1.7%. And a double counting could be possible. Electricity would be counted 4 times. So we will reach if we have a lot of electric cars, we will reach it very early. And these are the expectations. I don't want to go into detail, but you see, this is a part of these crop-based fuels. They will keep constant from 2020 to 2030. Also cooking oil and waste material will be constant. What's growing will be these advanced biofuels, and here it's almost nothing, but in 2030 we have these figures. What are these sources for these advanced fuels? You see all this list of these Annex A and Annex 9B will cover the used cooking oil and animal fat, but still going on, and a lot of research, but not really big industrial production today. And I'm quite sure that in the next 10 years, not so much will here, because the investment in such technologies is very high, and the future is unsecure. Nobody knows exactly what will happen. So just a question, you see my slides? Everybody see my slides?
Yes, we do. Everything working just fine.
So, and at the end, actually, we have to speak about sustainability, because we have this SDG, these goals, and are they really sustainable? Do they really save greenhouse gases? And that's the most important thing, of course. And I looked actually a lot of figures, hundreds of publications, and during the last, especially 20 years starting, and I looked to the European directive. In the annex of European directive, you see values for greenhouse gas saving potential compared to fossil fuel. And there are 2 values, so-called typical values and default values. If one producer produces, for instance, rapeseed oil of biodiesel, he could use this number 47% for his personal goals, or goals from the company. Each company has to reach specific greenhouse gas reductions, and they could use this number 47%. If you have other figures or the production processes is different, the typical value comes from already existing plants. But you could use either this, or if you could calculate everything, it's that. And you see here, these are rapeseed, soybean, palm oil, and you see the reduction is, we could say, something from this first generation, like 50%. Greenhouse gases, mainly CO2, but also N2O, nitrous oxide, is calculated because during growing, it's very important, especially for rapeseed. Therefore, it's not so good like soybean. That has changed in the last years. For palm oil, you have to look how you produce palm oil. And with methane capture on palm oil, you could also reach almost the same amounts. But if you look to used cooking oil, you have over 80% reduction of greenhouse gases. Animal fat, it's similar. And if you look to HVO, rapeseed or soybean, you see it's almost similar. So HVO soybean has more than biodiesel. You could ask why that's the reason. The reason mainly is coming that the use for biodiesel methanol, and methanol is coming from natural gas. But these figures are, in general, you can say you save something like 50%, but not this so-called indirect land use change. It's not included. It's a very complicated topic which I won't cover. This is also always the problem with this first generation, this ILUC, which is not considered because it's not really discussed in detail until now. So the last slide, I will show you something about new fuels. We have a lot of, very recently, and especially last 2-3 years, it was May 21, e-fuels. What are e-fuels? So could e-fuels save the combustion engine? Because there are a lot of discussions now from engine manufacturers say, no, we don't want to produce so much electric cars. We also want to keep our combustion engine, which is, totally developed, and we have a lot of cars in the future. Even if we change it to electric cars, we will still have in the next 50 years or 100 years a lot of combustion engine. Could we make these so-called e-fuels or synthetic fuels? The idea behind this, you take CO2, you take hydrogen, and make a fuel, as you see here. You take CO2, produce carbon monoxide, use water, produce hydrogen. You need a lot of energy, you see, by high temperature, catalysis, power, solar energy, and you need a lot of energy to split CO2 and split water. Then you make, with Fischer-Tropsch synthesis, so-called power-to-X fuels, or e-fuels, or synthetic fuels. Then you combust it and get CO2 and water. Here you get a lot of energy. And of course, you have to put the energy in this process at the beginning. So does it make sense? It makes sense if you use for this energy renewable energy. And the idea is to use surplus energy, surplus electricity coming from wind turbines, coming from photovoltaic systems. And it's a kind of storage of this solar energy. And therefore a big discussion, but it's more expensive. So you can say, how much more expensive is it? Is it 2 times, 3 times? I would say today it's maybe 10 times more expensive than traditional biofuels or traditional fuels. Maybe in the future, the goal is maybe to have a cost of double of the fossil fuels, double or triple. But there is no real industrial scale plant today existing. So coming to the summary, you see, out of numerous alternative fuel, only biodiesel, HVO, and ethanol are well established and have proven greenhouse gas savings. For the others, it has to be proven. The oil seeds produce oil and valuable protein, which is needed as animal feed. The advanced feedstocks are based on non-food feedstocks, waste material. They are promoted in the European legislation, however, the amounts are limited. And biodiesel compared to HVO has the advantage of lower processing costs and producing glycerol as valuable byproduct. And fuels produced out of surplus renewable electricity, so-called e-fuels, have a low overall efficiency, and they are far too expensive. And I would say as long as combustion engines are existing, and they exist for sure in the transport sector for the next decades, biofuels play an important role in climate policy. So with that, I thank you for attention, and I'm looking forward to any questions which I try to answer.
Thank you very much, Martin, for a very interesting presentation. I believe that we could go to the second talk, which will be related to second generation biofuels, and then maybe give a 10 to 15 minutes time for questions about this topic of biofuels.
Yeah, that's fine for me.
In your speech and Rafal's speech as well. So
that
gives me the opportunity to tell you that I am not the next speaker. In fact, the speaker is Dr. Rafal Lukasik. He is a good friend and a partner from Lisbon, from the Instituto LNEG. In Portuguese is Laboratório Nacional de Energia e Geologia. Maybe Rafal could give a correct translation to that afterwards, but let me introduce him. Rafal graduated in chemical technology from the Warsaw Institute of Technology. He's a PhD by the chemical engineering department from the University of Nova Lisbon, a senior researcher at the bioenergy and biorefinery units at the National Laboratory of Energy and Geology. And here you go. You have now your translation for LNEG in Portugal. He coordinates the biorefineries for biofuel program in LNEG. And since since November 29, 2021, he holds the title of full professor in chemical engineering, and he works in the field of biorefinery and conversion of wastes into biofuels and value-added products, with a special emphasis on employment of green chemistry principles. He has participated in several RD&I projects of national, European, and international dimensions, including projects with us here at UFPR and other Brazilian institutions. And he is author of more than 100 research articles, book chapters, and several patents. Rafal, my good friend, again, thank you very much for being with us today. The floor is yours. Please try to stick to the 25 minutes that we spoke about before.
Okay, thank you very much. Let me switch to the presentation. I hope you can see it. Yes?
Yes, all good.
Okay, so thank you very much again for a kind introduction. Good afternoon for me, at least, because I think most of the participants are from Brazil, so for us at least is already afternoon. Let me just hide this. So my name is Rafal Lukasik. I work in this National Laboratory of Energy and Geology in Lisbon, and today talk will be about the second generation biofuel. Maybe just a few words about LNEG. LNEG is a state lab linked to the Ministry of Environment and Climate Changes. It's divided in two laboratories, one of Laboratory of Energy, the second one is Laboratory of Geology and Mines. And on the side of Energy Laboratory, we have three main units, and one of them is biomass and biorefineries, where I do my main activities. So, of course, as we know very well, all these United Nations development goals are linked to development of circular economy, improvement of well-being, etc. So this is exactly what we are doing, and we can do this, for instance, using in many perspectives, using biomass as feedstock for chemicals, for products, for fuels. Of course, instead of using petroleum refinery, we can do this in something that is called biorefinery. You of course very know well this, and applying especially the green chemistry principles. But everything, as I said, is fitting in the new, well, maybe not new, but in the concept that is starting to be more and more relevant in the economy. And instead of having this linear economy, take, make, dispose, is to take it more to the circular approach. Yes, so to more the circular system where the feedstock, the waste starts to be a feedstock. So instead of being disposed, it can be reused. And actually, this concept is not very new one, because in already 1966. There were some especially in the economy part, there were already indication that circular economy is something that should be something natural, but it took some time before we really implemented, or we are trying to implement in the everyday life. Of course, we know that everything is also linked to, especially to the last few years, few decades, I would say, even tendencies to change to fight against the climate changes. As you can see on the left-hand side, already in 1912, people were seeing that the coal consumption affecting climate. So this is not something really new, but the first alerts were given more than 100 years ago, and even now we are still fighting with the same problem. So we are quite persisting in what we are doing, and we are quite difficult to change our habits. Yes, but coming to the biofuels is exactly what the subject is, especially from the EU perspective. Biofuels are not something new, and you know very well, and still biofuels are one of the priorities of European Union. The first at least legal aspects were discussed already in 1997, when the first white paper on renewable energies were published. Then we had the first directive for biofuels 2003, and then already what the previous speaker said, red directive, renewable energy directive in 2009. Then there was a quite important change in terms of indirect land use change directive, and the new one that is already in place, the second renewable energy directive, on working for 2021-2030. And I'm happy that the previous speaker discussed this issue, because this saves my time. But as you can see, what tackles the transport fuels, the EU minimum sub-target for transport is 14% by 2030, and each country can have their own sub-target. And for instance, for Portugal, this sub-target is 20%. So in general, Portugal will be above the average of the European Union by 2030, supposed to be. Although the numbers seems to be quite small, however, it's important to understand where we are, or where we were at least 2 years ago. If you take a look on the right-hand side figure, you can see that still only 5% of fuels are biofuels. So we are not talking about second-generation biofuels. We're talking about biofuels in general. So only 5% of the biofuels consumed for instance, in Portugal, but in Europe in general, are only for biofuels. So we are still 95% oil dependent. So you can imagine how far we are from what we supposed to have in 10 years in general, and what is the challenge ahead us in the next 10 years. And this is just a figure to show you how we see this will change, how the consumption, what is the roadmap for moving to different kind of fuels. As you can see, the oil, it's foreseen. It's a different way of showing what previous speaker said. You can see that it's expected that by 2050 we will still be at least in 1/3 oil dependent. biofuels will be counting more or less 1/4, and the rest should be electricity. Well, how it will be, we will see, but you see the tendencies that this is at least what some bureaucrats and technocrats were looking for, and we will see how we can be, if we will be successful or not by 2050. Of course, this can be done with the correct, with the GHG savings. And as European Commission is trying to be leader of these changes in the world, so there's not enough to put on the market new biofuel, but the biofuel produced in the particular installations has to fulfill this kind of limits, GHG emissions reduction targets, and depends on the when, from what kind of installation the biofuel was obtained, for instance. So if we are discussing about biofuels and biogas, and we are talking about the new installations, so to count on the national target, the new biofuel must demonstrate at least 65% GHG reduction. So this is how if you cross this information with the presentation of the previous speaker, you can see that not all of these biofuels will fulfill this kind of requirement. That's why it's quite important to understand where we are in the first and second generation biofuels. So this you can see that if you take a look on LCA well-to-wheel approach, you can see that starting from fossil fuel, that is more or less here on the top. I don't know if you can see the cursor of my mouse, but doesn't matter. But then you can see that the first generation is somewhere around 50% savings. So, and then if the new installation are in place, so they have to fulfill at least 65%. So basically the first generation biofuels will never fulfill this, because then you have to go to the second generation biofuels like syngas, diesel, from farmed wood, for waste wood, or ethanol, for instance, from sugarcane from Brazil, or ethanol from wheat, etc. So you see where we should go, in which direction we should go to get this high reduction GHG reductions. And of course, I would like to show you that this is not only just on the paper, but there are some kind of particular and practical examples. For instance, Scania in 2018 demonstrated the first Scania bioethanol truck. Of course, it using this kind of car truck, you can get a reduction of 90% of GHG emissions. Another approach is, for instance, with this kind of cellulosic bioethanol. This is quite something obvious for you, especially in Brazil. But I would like to pay your attention to the right-hand side, that it's not directly working on biodiesel, but it's a e-biofuel cell. So you introduce ethanol, second-generation ethanol to the system, and then it in the reformer it produces hydrogen that later on in the fuel cell can run your car. Yes, so you have on the exhaustion gases, you have water and CO2 coming, of course, from the reformer. So this is the way how you can use not only ethanol as in the combustion fuel, but turn it in your car into hydrogen to supply the fuel cell. And this is, if you look on the in the perspective of next 10-20 years, you can see what are the tendencies, what will happen probably with the development of technology. So if you look especially, for instance, for gasoline in Brazil, by 2017, the LCA, the full life cycle GHG emissions were around, let's say 100 grams CO2 per kilometer. And with changes in the technology, we can probably get around 60 or something like that. And only if you go to more advanced cars or more advanced situations like hybrid ethanol fuel cell, you can reduce emission and at the same time energy consumption per kilometer. So this is the trend, this is the tendency that we should follow to achieve the goals of European Union, and not only, but also in general in the world to reduce the emissions and and improve our performance in terms of energy consumption per kilometer. And some examples, for instance, of course, Brazil is very well known from the cellulosic ethanol, but also in Europe we have this, for instance, Clariant, where they have already opened some plants in Slovakia, Romania, Finland. So these are the second generation plants working in Europe, where they produce second generation ethanol from for instance from straw residues, from agricultural residues, etc. So there is a lot of things are happening, but as previous speaker said, investment is tremendous, so it's quite difficult and quite not very easy to make the real difference in this area. But coming more to the technology that Luis knows very well, we know, of course, that there are few approaches. Okay, for instance, you can have this cellulosic ethanol that all of them normally, all this technology starts with biomass, then you have a pre-treatment, and then after pre-treatment you get sugars that will, after hydrolysis, you can convert in case of cellulosic ethanol to ethanol. But for instance, if you are talking about other fuels, like for instance jet fuels, you can get through fermentation, different fermentation, you can get jet fuel that can be at least partial substitute of the commercial jet fuel. Alternatively, instead of going to bioethanol, you can get through the same approach, basically, some kind of chemicals. It can be through ethanol, then catalytic conversion to bio-based chemicals, or through different approaches of fermentation or bio or catalytic processes to get different bio-based chemicals like lactic acid, furans, and many others that can be later on used as a pivot chemicals for industry. But it's important, coming back to advanced biofuels, it's important to understand where we are and how we should look on that, because the technology value of that is quite steep, and we have to understand that this is quite difficult to pass. This investment is one of the obstacles, but not the only one. Yes, this was done on some projects on the positioning of FP7 supported technologies. It's a European program for project. It was some time ago, in 2016. So there are some changes, but definitively the cellulosic ethanol is the one that really passed this hill, and we are on the right hand side where we can really have a second generation ethanol. That's one of the very few technologies that can at least right now reach that level, and there are still a lot of them on this climbing side, and I hope in the next few years, next decade, with our researchers and investments help, we can be on the right hand side where the prices will be competitive. Let me maybe go to this slide. But to understand why still there is a lot of challenges, there are a lot of challenges for generally second generation biofuels. It's important to understand why, for instance, the second generation bioethanol is still not very cost competitive with, say, first generation bioethanol. Well, first of all, feedstock availability and supply. We have to have a clean and rather low cost feedstock. That we cannot forget that other sectors are also competing for the same sector, for the same feedstock, for instance, agriculture, animal feeding, etc., etc. Still, we have higher capex and OPEX cost, especially when you compare to first generation ethanol. Yes, because we have pre-treatment stage and enzyme hydrolysis, enzyme production. So these are two very relevant aspects. Also, normally, strains for second generation sugars are less performing than the first generation, and we still have this part that is well, we could say inert for the bioethanol production as lignin, but can be used for different purposes. Sorry, this is double. Okay, so addressing the first part, pretreatment. As we know, there are numerous pretreatment methods, and there are some novel ones, some classical ones like steam explosion, like acid hydrolysis, etc. But nevertheless, always the objective of the pretreatment is to disrupt the complex structure of lignocellulosic biomass. This way you can improve the cellulose availability by reducing, for instance, cellulose crystallinity. We can remove lignin. Also, we can remove partially hemicellulose, at least make it much easier to be hydrolyzed. But especially if we are talking about from the enzyme perspective, pretreatment should improve enhance the surface area for enzyme attack. Of course, there are a lot of challenges in pretreatment, of course, because if we are talking, for instance, about the physicochemical processes, there is always a issue of absorption versus adsorption. If we are talking about the processes with biomass, with large-scale equipment, we may have some problems in terms of, for instance, biomass supply, etc. So there is a lot of challenges in biomass pretreatment. I don't want to enter into details because this is very particular area. However, once we have this kind of process sorted out, then all the stages are much easier to be implemented. But nevertheless, there is a lot of challenges because we are working with the very diverse material, very often not very clean, and this brings a lot of challenges either to the research side, but also to the implementation side, on the mechanical part, on the automatization, etc. Maybe we can move to the most. This is something that probably Luis should say, not me, because he's the expert in steam explosion. But this is one of the most commonly used method, at least in Europe, for the biomass pretreatment. Steam explosion is just a process where you use saturated steam on the wetted biomass, and then once the process is performed, you simply blow up the biomass into the expansion chamber, and you get the biomass with more open matrix, and then it's easier for enzymes to act on this kind of biomass. And these are the examples where this kind of processes are used. For instance, some of them are acid catalyzed, some of them are uncatalyzed. So you can see they are around the world, some of them in Brazil, Italy, etc., in the United States, and many others. Sometimes they are using diluted ammonia, so there are some variations on that. Nevertheless, there are plenty of options and places where this technologies is used. Of course, pretreatment is one step. The other challenge, as I said, is enzymatic hydrolysis, and because of the cost of enzymes and the fermentation approaches. Again, there is a lot of work done, especially a group of Luis Ramos did numerous works during few decades, starting from very simple enzymes. Now we even working with next generations enzymes, and you can get enzymes either from commercially available. You can produce them on site. A lot of options can be studied. And also not only the enzyme itself, but also you can integrate the process of enzymatic hydrolysis together with fermentations. You see, these are just 4 examples how you can do this. You can do single hydrolysis and fermentation. You can do simultaneous saccharification and fermentation. You can do more complex processes where you, for instance, do SHF, single hydrolysis and fermentation, with clear mesh and membrane technology to separate, so to recover enzymes, and many others. So you see there is a lot of research and a lot of activities on this field. And especially on the enzyme side, as I said, enzymes are quite important element in terms of cost, at least. So a lot of companies working on development of new enzymes. For instance, Novozymes is one of them, and a lot of enzymes has to be, for instance, the newest one, salicylic CTEC 3 are one of the most recent one. However, Novozymes are working on developing customer-specific enzymes. So you can see that it's not that every enzyme can work for every kind of process, and you should always optimize it to particular application. Let me go to another slide. Another important aspect is that, for instance, if you use, for instance, fermentation and hydrolysis and fermentation together, it's quite important that you always pay attention to the solid content, because this way you can also increase your sugar availability and automatically ethanol yield, because only in these situations you can, at very high sugar availability, you can get economy feasibility of the ethanol production. And of course, enzyme loading is also very relevant, because you should always deal with as low enzyme loading as possible at maximum yield of glucose, reducing sugar release. Maybe I will skip these parts where we are talking about different options. I will just show you the last one, where you, for instance, as you can see, you can integrate second generation overall technology of ethanol production with the first generation. So as you can see, you have a lot of options where you start with biomass. I'm talking about the scheme below. So where you start with biomass, where you have the pretreatment with steam explosion, and you can have enzymatic hydrolysis. And partially, for instance, from the hemicellulose, you can from one of the fraction acetic hemicellulose fraction, you can get acetic acid as a side product, and then sugars from the enzymatic hydrolysis can go to the production of ethanol. So you see there is a lot of possibilities, a lot of options where you can also extract lignin, as it is on the upper side, on the upper image, where you can get lignin for the different approaches. And why lignin is quite relevant? Because lignin is up to now, normally lignin was discarded or used as an energy source to supply, for instance, the process of bioethanol production. But lignin is a very interesting compound, because it can be, as you can see, it's basically composed by these three alcohols. And right now, business of lignin is considered as 1 billion euro. So it's quite relevant, because you have applications of lignin in numerous areas, like resins, like glues, like chemistry, also biochemistry, and many others, including energy purposes. So lignin is actually a new mine where you can get a lot of applications. Of course, there's always challenge regarding the purification. Nevertheless, there is a lot of opportunities for lignin to be better valorized than just simple burning. And this is just a slide where you can see how in 2012 lignin was seen as potential feedstock. So you can get, for instance, by single production, you can get a lot of energy products or energy-like products, like methanol. Sorry, can be either a chemical or can be energy source. DME, ethanol, Fischer-Tropsch products, liquid gases. Then you have hydrocarbons, a lot of hydrocarbons from benzene, toluene, xylene, and many others. Phenols, oxidized products like vanillin, vanillic acid, some aromatic acid. So you see, this is something we are entering to some fine chemicals and materials or macromolecules, carbon fibers, polymer, and many others, binders, pharmaceuticals, and polyols. So you see, there is a very wide range of applications of lignin as a part to be considered, especially in the context of economic feasibility of the second generation biofuels. Because another important aspect is to what extent we can go with scale. Because as I showed you, for instance, if we want normally scale is working in favor of going down with the price. But there is another aspect that, as I said, for instance, lignin can be a very value product. However, there are just a few chemicals with markets enough large to absorb the production of other kind of chemicals. Yes, so it's not, we cannot only see, for instance, look on the economy of one product, for instance, second generation biofuel, but we should see in a broader concept, in a broader perspective, and see what kind of other products, chemicals, materials we are producing, and if there is a market for this kind of chemicals that where they can be applied, and there is a market that can absorb this kind of products. So this is quite important, and I want to show you, for instance, how we this is something that we did in one of the projects with in Eranet with Latin American countries, where you can see that once you have only ethanol, second generation ethanol, we never get NPV positive. But if you start producing other chemicals, like for instance xylitol, you can get quite easily a positive NPV. Or if you go to, for instance, oligosaccharides, you can get it even faster, especially if you increase the scale of the small scale biorefinery. However, then again, there's a problem. Whether exists market, do we have a market to absorb this kind of chemicals? In case of xylitol, probably there is, but oligosaccharides, that's always a question. How we can get it without losing the profit from this kind of oligosaccharides. So this is something that has to be always considered when we are discussing about the feasibility of having larger scale facility, for instance, for second generation biofuels in the biorefinery concept. But then normally we are not very taking care a lot on other products that has to be somehow, the other have to be somehow implemented somewhere without losing their high value price. So just maybe to, okay, it's a good time. So what we should do in the near future, medium large term. So should we consider that ethanol is an energy carrier for next generation transportation fuel? Well, basically yes, but we should also think about other alcohols, for instance, butanol, or maybe some other chemicals like fatty acid, long chain fatty acids. So ethanol is not the only one. We should always try to improve overall energy efficiency. Okay, so we shouldn't only think about the product, but we should also think about the maybe different feedstock. Can be cane energy, or can be dedicated crops, or we should change also something in the process, for instance, low demand biomass pretreatments, or we should integrate it with different approaches, with different recovery system. We should also think about different, not only about biofuels or second generation biofuels, but we should also look on the biochemicals and try to see a potential and where they can be implemented. Okay, so especially in the context of the large scale facilities, where, as I said, only a few chemical products can be implemented on the large scale and absorbed by the market. Lignin, we know very well that's a gold component, because in the past at least worked as an energy carrier for ethanol production or for second generation biofuels, but lignin starts to be a feedstock for conversion into high added value products from other than energy. Of course, there's another important aspect. Can we somehow avoid enzymatic hydrolysis step? This is something that probably Luis can help us answer this, but this is something that would definitively improve our cost efficiency process, cost efficiency of our process of the second generation biofuel production. Then, should we go to rather small scale processing that can reduce capital cost, or should we go to large scale processes? Then again, coming back to this capex, opex, how we should balance this in terms of only bioethanol production, or maybe we should look on the synergies on cluster-based biorefineries, that we should have not only biofuels as the main product, but we should see this in a broader concept where other products are produced, and then capex and opex can be divided into different processes and make the process, the entire biorefinery, more cost efficient. So there are a lot of answers to be addressed, a lot of questions to be addressed, and basically that's what I wanted. Okay, my timing is perfect. So thank you very much, and if you have questions, please feel free to ask, and thank you very much.
Thank you, Rafal, for a very interesting talk, complementary to what Martin has addressed in his own presentation. Are you staying with us until the end, Rafal?
I will try so, although I have a meeting in 1 hour, so at least by next 1 hour, yes.
Okay, so in this case, I will open up the floor for questions for a few minutes, and so that if you and Martin have anything else to do, in your schedule, you may leave without frustrating the audience in terms of questions that they might have. We don't have a lot of questions in our chat right now, but there is one addressed to Martin and maybe addressed to Rafal as well, regarding the use of used cooking oil. This question was sent by Maria Juliana Suota, and she is asking about used cooking oil as a feedstock for second or third, but maybe second generation biofuels. And we heard a lot today about the usage of used cooking oil, and two questions are like within her comments about waste cooking oil. The first one is cost, and cost also includes logistics. So to operate in large scale and supply a market that is growing steadily, would used cooking oil or waste fats and greases be enough to meet the demand? And would this concept of being cost zero remain for the future? I give you one example. In the past, some fats, animal fats here in Brazil were very competitive, but nowadays they cost like twice, 3 times as much, and they are not accessible anymore for converting them to biofuels, being biodiesel in whatever source it is. So maybe Martin, can you comment on that in terms of the question about using cooking oil? What is the specification involved? Can we actually fit this into the logistics that is easily implemented? You guys have a tremendous work in Graz in terms of logistics. I remember seeing those collecting tanks all around town, for people, to drop their fats and used fats and oils, and so that you could process it in the Styria facility. So could you enlighten us a little bit more with this situation of used cooking oils and and spent fats?
Yeah, fine. I'm glad to try to answer the question. So maybe you have to distinguish between used cooking oil and animal fat. So that's a different topics, starting with used cooking oil. Well, the market is already existing. So I would say 95 or almost 100% of waste cooking oil coming from industry, that means restaurants and big kitchens and so on, they have to collect, of course, and they have to deliver it to waste collectors, professional waste collectors, and most of it is going directly to the biodiesel production. I think it's the most important use of used cooking in Europe. So I can say that mainly for Europe. And here the question is, are the transportation costs too high and so on? Of course, it doesn't make sense to make a plant in south of Italy and delivering oil from north of Europe. But you've seen one of these biggest plants already existing exclusively for used cooking oil. That's in Amsterdam. In Amsterdam, the owner of this plant, it's now Energia, but it was before a collector of used cooking oil, and he was covering the market from whole Northern Europe. So it means Belgium, Netherlands, and so on. They have a lot of used cooking oil for French fries. And this is existing, and the transportation costs are not so high. You know that cost on the road, well, a ship is of course cheaper, but it works. So if you have an area of about 200, 300 kilometers, it's or even more, 500 kilometers, that's fine. And these industry is existing, and what is missing is still there is a lot of amount of households, cooking oil, waste cooking oil in households. Here, the collection, Luis already mentioned, we had a lot of trials to improve this, but now it's a little bit changing. So we have some supermarkets here in Graz, for instance. 2 days ago was a supermarket. They have at a big supermarket a collection system for used cooking oil. Here you can go with your small can or bottle, whatever, and give it away. You wouldn't get any money, but also you don't have to pay anything. And this directly goes to the biodiesel producers. So I think in the future we have limited amounts. I have told you the figures for Europe. We almost reached a maximum of or the top of this collection system. Missing, of course, is most of the oil coming from here. We have to promote it, and to promote, say, if you put it down the drain, you had the problems like in London, and there's a lot of costs there. For animal fat, maybe situation in Europe is different to Brazil or US. I always are pushing, trying to push production of biodiesel from animal fat, and I know also from the SSA it's not available, so we don't have enough, and the price of animal fat, even waste animal fat, it's a problem. So it's too high if you have uses for that, and if you use it as animal feed, for instance, again, so that then the price is going up. But in Europe we still have these dangerous wastes of an arbitrary this special risk material, and here you don't have any you have to pay for it to get rid of it. If you are a rendering company, then you have, and therefore the chance that this is used as starting material for biodiesel is quite high. And there are already 4 or 5 plants in Europe existing, the biggest one, Energia, but also in other areas where they are in Germany, in France, big plants. And here the price is okay. You can't use, of course, animal fat, which could be used for food. So it's impossible because here the prices are very high. But this risky material, which even can't be used as animal feed, I think that's cost competitive. So but you would say this market is existing and could be a little bit expanded if you could collect this cooking oil from households. But
Great.
of course, we have a limited amount. That's here.
Thank you very much, Martin. A quick one for Rafal. What about the promotion of ethanol in Europe? Is it well accepted by fuel producers and engine producers? Is the possibility of adding ethanol into diesel engines been thought of? Is it limited, or can you tell us something about it? And also, I'll add something else. There was one figure in your presentation given by Gonzalo here in Brazil, showing a plug flow reactor stuck with biomass. You'll have to tell us more about that figure. You know, you won't escape without telling us what the hell that is telling us. So go ahead.
Answering your question, the first one about ethanol. Well, that's there are legal limitation in terms of adding ethanol to biodiesel. So as far as I'm aware, there are no considerations in this area. I think the only option is like fatty acids, FAME, to be added to biodiesel. That's the only legal aspect. So from this perspective, ethanol cannot be diesel cannot be blended with ethanol. Yes, so only can be added to gasoline, and that's it. Yes, and I think I'm not sure how it is in Brazil, but most of these aspects are regulated by the combustion diesel developers and those who are selling cars, and they are putting limits because they are, well, you know very well that this is a very well protected market, so they don't want to introduce something that is already in place, fossil fuels, and they don't want to change a lot in this. Although there is a lot of push from other sides to increase the amount of the percentage of ethanol to gasoline. But generally, ethanol is welcome, and as you can see, this is one on the slide that I showed. This is one of the first that actually passed this value of that. So this is one of the most advanced, most developed technology. Although there are still some room for improvement, but nevertheless, this is the technology that is the most mature among all the second generation technologies. And because of that, it's natural that companies are more eager to invest in this approach than, for instance, going to for instance, fatty acids to jet fuel, etc. Because a lot of still has to be done by us as researchers, and the implementation, even having first of a kind installation, is still far ahead. So there is a lot of aspects on that. Of course, ethanol. One of the options for ethanol is also to use ethanol as a feedstock for other energy carrier, and by the chemical conversion of ethanol to other chemicals and working as a fuel additive, then yes. But pure ethanol, only gasoline, blending with gasoline is acceptable. And
you tell me about that a reactor later, okay? If I because we're running out of time. Yeah. So
okay.
Yeah, you tell me later about it. So without further ado, I'd like to thank again the two first speakers, and we move on to the next Professor Júlio César de Carvalho. He's a professor of the graduate course in bioprocess engineering and biochemistry at Federal University of Paraná. He obtained his PhD from the Federal University of Paraná in 2004. And after joining UFPR in 2006, he has worked mainly with bioadditives, especially biopigments and lipids, bioprocess modeling, microbiology, biotechnology, bio-based chemicals, and engineering education. He has published 85 papers, 39 book chapters, registered 22 patent claims, and has been involved directly in the advisory of 4 doctorate theses and 11 master dissertations. He's also engaged in research that supports the scaling up and integration of bioprocesses for microalgal biomass conversion and bioadditives production. With this introduction, I pass the floor to you, Julio. Thank you very much for accepting our invitation. You have 15 minutes, please.
Okay, thank you for the kind invitation and the introduction, Professor Luis. And I salute the other participants of this panel. Good morning and good afternoon to the others at the other side of the Atlantic. And let me share my screen here. Here, screen. Start broadcast. Luis, please confirm that everything is okay, that you have the slides on your screen.
Looking good.
Okay, perfect. So if I talk too much, colleagues, you know, as a professor, I live from talking since 1992, and we are used to well, sometimes extend too much our ideas. But here we will present very shortly, I hope, some ideas on not on broad production of microbial biodiesel, but a case study. Right, it's a case study of biodiesel from yeast. That's actually a project, a 10-year project that I sort of saw a bit, but it was conducted by Professor Sokol, which was to give this talk with me, by the way, but he could not, and sent his excuses. And it was a very large project with UFPR and FINEP and the participation of Orofino Agribusiness. Right? And very interesting, a lot of challenges, and it led to a good result, as you will see later, right? So in terms of the research team that we have today on microbial lipids, we have 6 researchers that are presently working part-time in this, part-time in other projects, but we have a few colleagues, which are in several places now, that participated since I guess 2008, right? And I don't have a picture of this specific team, but I have a picture pre-COVID of part of the team in the bioprocess engineering laboratory. So this is a multi-professor, multi-usuary laboratory led by Professor Sokol, which is here at the center, or PI, right? But also with the participation of a few other professors, 9 professors, right? And this picture has graduate students. There's one IC student here, but the others are all PhD and master's students. And part of these colleagues here worked on this microbial biodiesel project, right? In terms of lipid content, we tend to think of microorganisms in terms of its lipid content, and that is one of the reasons why microalgae seems so very good for microbial production, because they can accumulate very high concentrations of lipids, especially in nitrogen or phosphate starvation phase in their growth. But we have a problem of productivity, right? That's the challenge in microalgae. I also work with, actually work much more with microalgae than yeast. And I love these green microorganisms, but in terms of productivity, we are far from producing something that's sustainable, right? While when we talk about yeast, you know, bioethanol is produced by yeast. And these little beasts are very, very fast in their growth. They have an accelerated metabolism. And in the case of production of lipids, we can have high titers of biomass with fair concentrations of lipids in the cells. So when we make an economic analysis of the process, it sort of works, right? The only problem is that while microalgae produce their own organic molecules from photosynthesis, yeasts do not, right? So yeasts, you have to feed them some sort of sugar. And in this case, in this project, we use, you see, sugarcane juice, right? Another problem in terms of the production of lipids from microorganisms is that the process is to have a high quality oil is a bit complicated. This is a simplified flow chart for the main operations that we have when processing a fermented broth that could be either microalgae or, for example, yeast, right? But the problem is that with microalgae here, we have a very, very dilute solution, right? So biomass recovery is a first problem. You have too much energy input here, and that's why so many people work with flocculation of microalgae to improve that. But then you have perhaps biomass washing, and then a step of drying, and a bit of grinding, but drying, which will require energy. And why do you need that? Well, because to extract lipids from wet biomass is complicated. It can be done, but it's complicated. You have the formation of micelles and emulsions, and extract part of the proteins in the process. It's a bit messy. So these initial steps complicate the process, right? That is why such a process, it's usually more useful for lipids that have some other value than just biofuels, some nutritional value. And that is why also this topic of SDG 7, using yeast in this case, sort of touches other objectives of the millennium. Because if you think of objective 2, which is to end hunger, but also to have good nutrition. The objective 3, which is to have a better health, right? Which also passes through nutrition. And then the others, you have life underwater, you have clean water, you have, of course, this one in energy. So these things are all linked. And we think that producing not only biofuels, but lipids from microorganisms can help in several of these aspects. But turning back to the production of biodiesel, this specific work here regards the production of biodiesel from the East Rhodosporidium toluloides, which is you can see here, it's an orange microorganism because it produces also carotenoids in the biomass. And this one was screened from more than 100 yeast strains at Orofino and UFPR because of its productivity and its lipid content, right? So screening is it's a key to sustainable and competitive processes in any area that uses a microorganism, right? And this microorganism was cultivated just with addition of nitrogen source, urea, to sugarcane juice. First in small scale, bench flasks, aeromeric flasks, and then in larger ones. This table here shows the comparison in terms of lipid productivity for several several papers that describe the production from Rhodosporidium toluloides. And we see that there are interesting attempts of using hydrolysates and residuals, glycerol, for example, but the best productivities are with sugars, right? So the best one is this work that we're describing here. It was published in 2017, and it's now on the process to be transferred to a company, right? But we also have, this is very notable, but you have to see the details in the paper, in the original paper, have here a very high productivity too, right? But in small scale, from cornerstone hydrolysis. So there's a lot of space to work with culture media in this case. And why did we use sugarcane juice? Because it's very cheap. It's produced en masse. We already have industries dedicated to producing biofuel from that in Brazil. So it was a logical step to try, and then we will see it was proven to be economical, right? So this is the composition in the left panel here, the composition of fatty acids from rhodosporidium toluloides. You can see that it's mostly monosaturated and saturated fatty acids that gives fairly good biodiesel. And for reclaiming that lipid that is inside the cell, we have to have pretreatments. So, and that's another step that we have to work in terms of energy, focus on energy. It's possible, for example, it's possible to just disrupt a cell, right? Just break it with mechanical equipment. But this, although it will give the fractions mostly unaltered, it's very energy intensive. You cannot think of ultrasonication, for example. It doesn't work in large scale. You have to use mechanical homogenizers adapted from milk production, for example, or milk industry, or microbead grinders, and the energy uses is high. Of course, in the end, it will still pay, but it will give a very expensive oil. So other options that we have are enzymatic hydrolysis. Again, this is expensive. It works for some microorganisms, and especially if you want edible oils, that could be a good, interesting, good thing to do. You can dry that and then make the extraction with solvents, for example, and you can leave all that behind and just pyrolyze the biomass to reclaim the energy as some sort of bio-oil, which is fair, but is not biodiesel, right? So in terms of what was done in this specific case is that after some tests and in small scale in aluminum flasks, this process was scaled up to 10 and 100 and 150 actually, and 1,000 liters. This is the useful volume of the reactors. The reactors are a bit bigger, and I would like to draw your attention to the production that we have, right? In the 1,550 and 1,000 liters. Similar productions, a little less in the 1,000 liter reaction, perhaps because of oxygen transfer in the scale up, and with fair productivities, right? And in terms of lipid concentration, also some repeatability. This is concentration in the medium. When we go to a fed batch strategy, which is to use the same reactor, but continue adding sugar, we can reach higher biomass productions, a little bit more time, of course, but higher biomass production and a higher titer of lipids in the culture medium, right? So similar productivities, around 0.40 to 0.44 grams per liter per hour, but in a single equipment in the case of fed batch. So it was an improvement strategy. And these are photos of the reactors. You can see here bench scale reactors with the yeast being cultivated in a controlled environment, and then a larger scale reactor which is less sophisticated. So maybe the control here was a bit worse. That's why we may have had a little less productivity, but still similar results. And here a curve that shows the points where we had the feeding of extra culture medium, right? I understand that I don't have too much time, so let's proceed fastly. What we did in this case was then to harvest the yeast. It sediments naturally to the bottom of the tank, but then treat it with HCl this is not very common, because when you make some sort of partial hydrolysis of the biomass, you treat with in this case 1% HCl, you have some alteration of the products, of course, and the fatty acid that part of the lipids will give rise to free fatty acids. But for this process, it was the best choice, because the other alternatives were too energy intensive. And the oil that was production, it has also, it's actually a quite good aspect. Let me show you, because I have here 2 bottles. Here. This is raw oil, right? From after the harvesting and the separation of oil with solvents from the biomass, and this is the biodiesel, right? But the best part is that this biodiesel was tested. So I'll go back and take a little more time to show you on screen, to show the results of the application of this biodiesel, the tests in diesel motors. So here it is, right? This was actually tested. So these are performance parameters for biodiesel, not pure biodiesel, but B5 and B20. Compared with B5 and B20 using soybean oil, the reference oil. And what we have seen is that, well, we have actually a better performance in all situations, but what is most interesting here is to see that the emission of CO was also very low. So these two down here are the B5 and B20 from east, the single cell oil, while these are biodiesels B5 and B20 using the reference mixture, which has soybean biodiesel. So it's a good oil. It's a good oil, and if we improve the process a little bit, it may fare even better. And we did some sort of preliminary analysis. Preliminary because to make a fair, complete analysis, economic analysis, you have to compare both capex and opex, see some internal return rate, and check whether investment in such technology really works. But for a preliminary evaluation, just to check what you are putting in terms of materials and energy already gives an idea, because what makes a large process be profitable or not is not the capital costs. Not that they are to be despised, but the capital costs can be absorbed by a process that has low operational costs. So that's something that we have to pay attention, and it's fair to make a preliminary analysis on that basis. And from that, we see that if we have 1,000 liters of fermented broth, that will give rise to 22 liters of that oil that I showed you, and then 21 liters of biodiesel done by traditional esterification and transesterification reactions, right? And computing the costs of the raw materials in terms of the cost of the sugar. So this is 11.14. That was 2015 is evaluation. So a bit more now, but anyway, not too far from that. And a bit of urea, we will have a cost of the medium that would be around 26 cents per liter of bio oil, right? And we have a lot of energy costs, of course, because even using a chemical breakdown with cheap HCl, still we use it. We use energy. We have energy input in several steps that are shown here, and that will add to the cost of the biodiesel. But it still is relatively cheap if you compare with soybean biodiesel. And when we check what can be done with the land in terms of production of energy, we see that production of biodiesel with microorganisms makes a lot of sense, because if you check here, the yield of biodiesel from sugarcane, but then fermented by yeast and extracted, we will have around 4,200 liters of oil per hectare. If we compare that to palm oil, which is one of the most important oleogenic crops that we have, palm oil, I guess, produces around 5,000 liters per hectare. That's not too much more. So this is a very good result. And that's because sugarcane is, it's a very fast growing crop and very efficient in accumulating sugars that can easily be used then by the yeast. Right, and this production is 6.3 times what we can do with soybeans, for example. So it is a interesting technology, and that's why we're now negotiating it. And that was in case someone is interested and wants to check one of the papers that describe this. You can find it through your preferred aggregator of papers, right? So a bit more of the publications. And with these, I will end. This is just some patents that are associated with this line of work. And reinforcing that, because I know that it should have a panel on microalgal biodiesel and microalgal biofuels. We also believe here that microalgae have very good potential, because when we compare what can be done with 1 hectare of microalgae, 1 hectare of sugarcane, they are very similar in terms of their very high productivity, and it's far superior than most other crops. But sugarcane produces sugar. Everybody loves sugar. Microorganisms love sugar. That's easy to transform in other things. While for other technologies, well, we have to work a lot, and maybe we'll be seeing something more real in terms of biodiesel from algae in the near future. But right now, many of the companies that started those processes went on to produce, as you may know, other biomolecules from microalgae because of the value, because of their aggregated value that compensates for the production that has high costs. Okay, so I hope that I didn't exceed too much of the time, Professor Luis, and thank you again. Congratulations to all for this very interesting meeting. Not only this one, but I have to say this with the CU initiative is a very, very good idea. It's a universal goals, a university and universal project at Sprint. We just have to do it again in the next year and make a little bit more of divulging of I don't know. Even in the page of the university, it's not appearing.
Yeah,
right?
I totally agree. Well, the only comment I will make about your presentation, which was of course very good, is that Martin Mittelbach sends congratulations to your work. He was very impressed, and he might want to talk to you about this afterwards, but you know, we don't have time right now. We have to move on to the next speaker. Our next speaker is Dr. José Viriato Coelho Vargas. He holds a BSc degree in Mechanical Engineering, Biology and Administration, MSc in Thermal Sciences, PhD in Mechanical Engineering from Duke University, USA. He is a member of the Energy Committee of the Brazilian Ministry of Science and Technology and Innovation. He is a full professor at the Department of Mechanical Engineering at Federal University of Paraná, and a visiting professor at the Mechanical Engineering Department and the Center of Advanced Power Systems at Florida State University. His main ongoing projects are related to the development of new fuel cells, new absorption of refrigerators, thermal management of all electrical ships, cabinets for electronic packaging, and the use of infrared imaging in engineering and medicine. He's also the head of the Sustainable Energy Research and Development Center at UFPR, which is focused on microalgae biorefining. He's the technical editor of Thermal Engineering Journal of the Brazilian Society of Mechanical Engineering and Sciences, and has published 147 articles so far in the ASI Web of Science with an H factor of 26. Please, Vargas, could you open up your camera and upload your presentation and go ahead with your speech?
Can you guys see me already?
Perfectly. Please.
Okay. So can I share the screen?
Yes.
Should I share the screen? Am I authorized already, Luis? Okay.
Yes, you are.
So let's do it then. Do you guys see my presentation already?
Perfect.
My slides. So good morning, everybody. Thank you for the invitation, Professor Luis Ramos. And I'm here to talk to you about the Renewable Energy Global Challenge, which is the title of my presentation today. So let's not waste any time and get into business. So I start by saying, listing to you guys the humanity's top 10 problems for the next 50 years, according to someone that I think it's a very important scientist. He's already passed, but you might remember him. His name was Richard Smalley, and he was a Nobel Prize in chemistry in 1996, one of the inventors of the carbon-60 carbon-60 substance, and he listed the top 10 problems as number 1, energy, number 2, water, number 3, food, number 4, environment, number 5, poverty, 6, terrorism and war, 7, disease, 8, education, 9, democracy, and 10, population. And he passed it in 2005 and updated his data to current days. So you see that in 2019, we had a 7.7 billion people population in the world, and we expect to reach in 2050 9.5 to 10 billion people. Well, in this slide, you see what we mean by non-renewable energy resources and renewable energy resources. So the world is currently dominated by fossil fuels, but it's in a transition to replace fossil fuels with the so-called renewable energy resources for the sake of preserving our living environment, our world, in other words. So the fossil fuels have limited supplies and will require a long time to replenish. They are well known: nuclear, coal, oil, and some others. And solar energy, wind energy, hydro energy, and bio energy supplies, and some other processes from the nature are replenished naturally in short periods of time. So it's much more desirable from a first point of view to use renewable energy resources. Well, in that sense, so for that to be feasible, technically and economically viable renewable energy generation and storage are still major hurdles to be overcome. So that shows we need research on that. And this article from these authors, Angelis et al., published in this journal ACS Energy Letters in 2018, shows us that there are some, we could summarize the areas to do research so that renewable energy could be a reality and replace fossil energy in the world, are energy materials, solar cells, storage batteries, solar fuels, display devices, theory and computational modeling. This graph also shows a forecast for the energy consumption in 2052. In the vertical axis, you see the megatons of oil equivalent energy in terms of that per year that will be required in the next years, and starting from 1970 to 2050 on the horizontal axis. You see the participation or the contribution of renewables, nuclear energy, coal, gas, and oil. You see an increasing contribution of renewables in that graph. That's what is expected. And there are some hypotheses that were utilized to produce that graph, which is authored by this author on the bottom of the slide, Renders, and he assumed that the world population will start to decline from about 2040. Computer models were utilized to make sure feedback effects were not overlooked. And energy efficiency is assumed to continue to increase, which is also a reasonable assumption. And so, as a result, in 2050, we have the so-called terawatt challenge. So we will need 23.2 terawatts of energy, which is equivalent to, in terms of megatons of oil equivalent, each terawatt hour is 11.63 terawatt hour corresponds to 1 megaton of oil equivalent. So it's a unit of energy defined as the heat released in the combustion of a ton of crude oil. So it's approximately 42 gigajoules. So what do we mean by the energy revolution? We mean the terawatt challenge. You see on the graph on the left, in 2003, the world consumed 14 terawatts, which means 210 million barrels of oil equivalent each per day. And you see there the distribution: oil, coal, gas, fission, biomass, hydroelectric, and solar, wind, geothermal. So you see that the participation of renewables were still very low. What's expected for 2050 is a reduction, a drastic reduction in the participation of fossil fuels in the energy matrix. So solar, wind, and geothermal energy are expected to increase by a large factor. Hydroelectric, not too much, because we have natural limitations. Also biomass and fusion, fission are expected to increase too. So what was the basis of prosperity in the 20th century? It was oil. So it's still a question to be answered in the 21st century, what will be the basis of prosperity. We are still working on that. That's what the author, in this case, Ismaili again, tried to explain with this graph. So what's the general scenery? We see that hydroelectric energy is almost tapped out. Biomass has some criticism, and mostly due to compete with global food and water. Also, fossil fuels will soon deplete and become environmentally unacceptable. Nuclear energy, fission, fusion, and the spontaneous decay of uranium in the rocks also could be considered as nuclear, and then geothermal. And we see that the sun as a great hydrogen fusion reactor will have a large participation in that picture. You see that 165,000 terawatts of sunlight hit the Earth every day. But there is a big problem. Technology for cheap energy is required. That means low dollar per kilowatt hour. Can we do that? That's a question to be answered. So you see there that on the figure on the right, the Earth shown for size comparison with the sun. Proceeding with renewable energy, this study by Lewis in 2005 in the California Institute of Technology proposed some interesting aspects. We see there in the slide that the world, the continents, different from somebody could expect, not the entire area of the surface of the Earth's surface need to be covered to produce the necessary energy. So let's make this exercise. If we think of 10% efficient photovoltaic cells to comply with 2 kilowatts per person for 10 billion people, we would need six boxes, as shown in the figure in red squares, at 3.3 terawatts each. So that would make 20 terawatts of electricity with a 30% efficiency conversion, meaning we would need these photovoltaic cells to be hit by 60 terawatts. So photovoltaics are not impossible in that sense. That's the message from the author. According to Ismaili, what would be the required renewable energy nanotech revolutions? So we list there some of the possibilities. Number one, photovoltaics, but cost would need to be dropped by 100-fold. And photocatalytic reduction of CO2 to methanol is another possibility. Direct photoconversion of light and water to produce hydrogen. Fuel cells also would be interesting. However, number 5, we see that we will need hydrogen storage. And for that, lightweight materials for pressure tanks and liquid hydrogen vessels. Battery supercapacitors, flywheels, power cables, meaning reduce size of power cables, and superconductivity will definitely play a role. Nanoelectronics, thermochemical catalysts to generate hydrogen from water, sustainable hydrogen in situ generation, nanotech lighting to replace lights, nanomaterials, coatings, and CO2 mineralization schemes that can work on a vast scale. So this presents one possible list, but many other types of research need to happen so that renewable energy could be a reality to cover, to comply with the need of humanity in the near future. In that direction, our project at Federal University of Paraná presents a possible solar solution, which is our plant, which is a sustainable biomass and energy from solid garbage. And you see in that schematic diagram a simple sketch of what we have so far. And we divided in different modules. And we use microalgae. We start with module 1. So large compact photobioreactors to grow microalgae using sunlight with photosynthesis, and then generate biomass to go to module 2 after flocculation, centrifugation, and drying. And you see there challenge of energy supply for doing those processes. And why not? Direct hydrogen from microalgae is also another possibility. And so that's what we are trying to do. So directly from the photobioreactors, the microalgae have this possibility. And in module 2, the production of biofuels from microalgae biomass after drying with lipid extraction, one could obtain fatty acids, and the fatty acids will produce the well-known biodiesel. However, with the unsaponifiables, meaning the pure hydrocarbons that the microalgae have, after fractional distillation, long-chain alkanes can be obtained. And that would qualify this biofuel as the so-called green diesel. The challenge in producing such fuels is economic, mostly economically, and we're still working on that. Module 3 also shows that the defatted biomass after lipid extraction could also be used as pigments, animal feed, and other valuable products. And that's what we have been doing too. And what would supply the microalgae to grow? Here on the left, you see module 4, the possibility of using the energy after municipal waste incineration, solid municipal solid waste, so we can produce emissions to feed the microalgae, and also heat to produce energy directly from a Rankine cycle. So combining all those initiatives, this plant has been built and is under operation. There you see a shot of the appearance of the biomass that we collect from the photobioreactors after centrifugation. And then you see there the incineration facility where the solid residue is incinerated to produce heat, and from that steam generator on top of the incinerator, heat is transferred to the Rankine cycle plant. so that this steam turbine produces electricity in an electric generator. On the back of the incinerator, you see how the emissions are directed. First through the boiler, and then they go through these pipes until they reach a fixation column on the right. And from the bottom of the fixation column, it goes up, exchanging mass with a stream of microalgae cultivation medium that goes from top to bottom, so that in counterflow, the mass transfer is maximized. And in this way, the emissions, the toxic emissions from the bottom are cleaned up and leave the fixation column ready to be dumped into the atmosphere in an environmentally correct way. So it's a 9-meter tall fixation column. And this sketch shows what happens. Solid garbage gets in, also degraded liquid effluents, and then the sustainable plant treats the emissions, producing treated water and ashes that go to the cement industry, and also the microalgae biomass that is utilized to produce biofuels, biomaterials, and co-products, but also electricity, heating, and cooling. So the conclusions are, we definitely think that microalgae could be a possible solution for a sustainable world. They are organisms that transformed the inhospitable conditions of our planet into a favorable environment for life. The emission injection that happens in the fixation column that I have just shown you is fixed in the column, and oxygen is produced, and the NOx and also other elements of the emissions, toxic elements of the emissions are fixed. So there is potential of microalgae to treat hazardous emissions on a large scale in this type of equipment. However, multi-generator systems and environmental remediation and microalgae cultivation should be combined to use microalgae in an advantageous way. Finally, and last but not least, we should state that there are still major technological challenges to be overcome to enable the industrial use of microalgae, and certainly optimized systems will be needed and need to be developed. So that's, in a few words, what I wanted to say. And I would like to say thank you, and I'm available for questioning to whoever wants to know a little more about what we are doing.
Thank you very much, Vargas, for a very interesting talk. We'll leave questions for the end of the session. You know, we won't have much time because we are running late. I'll have to move on.
I believe I did not use it too much time, did I?
No, it's okay. It's okay.
It's okay.
We move on to Professor Claudiney Soares Cordeiro. He's an assistant professor at the Department of Chemistry of UFPR, where he has been lecturing since 2009. August 2019 to July 2012, he was a visiting scholar at the Department of Forest, Rangeland, and Fire Sciences at the University of Idaho under a print scholarship given by the internalization program of UFPR. He received his BSc degree in chemistry in 1999 and his MSc in engineering in 2003. was obtained in chemistry in 2008. His research interests include renewable resource chemistry and heterogeneous catalysis.
Stop sharing my screen, Luis.
So Vargas, Claudiney, thanks for being here. The floor is yours.
Thank you, Luis. I'm going to share my screen. Okay, do you see my screen, Luis?
Not yet. Maybe in a few seconds. It says here that you have shared your screen, but I have a block.
I can't see anything either.
Yeah. So try it again.
I will try. It's 1 minute.
Yes, good now. You're good.
That's okay?
Yes.
Okay. Thank you, Luis. I was a visiting scholar at the University of Idaho between 2019 and 2020. And I worked with Professor Cheng's laboratory at the Department of Chemistry for production of graphite from University of Idaho thermalized asphalt reaction, or guitar. Guitar has been produced in Idaho for over 10 years, and guitar is a material composed by a few sheets of graphene. However, guitar has...
Claudiney, I'm sorry to interrupt you, but I see your screen, but it's not on presentation mode. So try to hit the presentation mode and see what happens.
Okay.
I see your mouse. It's moving from one slide to another. I see the subjects now, but still not in the presentation mode.
Okay. I will try other.
For some reason, it's not coming.
Do you see now?
We see, try the presentation mode.
Okay.
It's still black, man. We can't see it. I don't know why, but when you hit the presentation mode, it turns black.
Black.
I don't really know why.
I don't know what's the problem. Now?
Working now.
It's good?
Go ahead, yes.
Oh, it works, yes.
Oh, thank you. Well, guitar was produced in Idaho for over 10 years, and guitar is a material composed by a few sheets of graphene, to see here. However, some properties of guitar are different from other materials containing sp2 carbons. And guitar has chemically modified to obtain brostoluric acidity, and acid solids were used as heterogeneous catalysis in esterification reactions. The chemical modification of the solids and the esterification reactions were carried out in Professor Armando McDonald's laboratory at the College of Nature Resources. During this period, I received a scholarship from Brazilian government through CapSprint program, and all necessary infrastructure for work in the United States was provided by University of Idaho. I'm going to talk a little about alternative routes for biodiesel, and I will mention some common methods for graphene synthesis. I'm going to talk a little bit about guitar synthesis, about obtaining acidic solids from guitar, and finally, I will present some results of the performance of these acidic solids in esterification reactions. Biodiesel is an alternative fuel, has been widely used, and biodiesel is production for alcoholization of triacyl glycerols in homogeneous alkaline medium. And the use of edible oils as a source for these triacyl glycerides, it's quite common, since they have low levels of water and acidity. Thus, the cost of raw materials makes biodiesel more expensive. Then frying oils and other materials could be considered an alternative for biodiesel production. However, the high content of free fatty acid and water, which is common in these raw materials, hinders their processing by classical method for biodiesel production. Among the common alternative processes, we can mention the esterification of free fatty acids, followed by transesterification in alkaline medium of remaining triacyl glycerides, and simultaneous esterification and transesterification in acidic medium, and the hydroesterification, hydrolysis, followed by esterification. The homogeneous process requires several purification steps that raise the price of biodiesel. An alternative that has been considered to minimize this problem is the replacement of homogeneous catalysis by heterogeneous catalysis. And compounds containing sp2 carbons, such as graphite or graphene, chemically modified to develop Bronsted-Lowry acidity, can be potentially used for the production of biodiesel. The various methods for synthesized graphene can be divided in two blocks: top-down destruction or bottom-up. It's the opposite. Top-down destruction or bottom-up construction. I would like to draw your attention for the chemical vapor deposition, because this method is used for synthesis of material with properties similar to guitar. Chemical vapor depositions decompose hydrocarbon gases and other biomass materials to grow graphene sheets on metallic catalysis at elevated temperatures, as you can see in the figure here. This is a simple system that was used for a guitar synthesis a few years ago, 10 years ago, I think. The system was hit about 50 minutes. The use of some materials for deposition of graphene is optional. This is because graphene can be deposited in porcelain plate. The decomposition temperature was estimated at 615 degrees Celsius. I would like to highlight some important aspects. In the process for production of guitar, the decomposition temperature of graphene is lower than chemical vapor deposition. Deposition takes place in the presence of oxygen without use of catalysis, and the equipment used is simple. In this image, we can see the graphene sheets. The materials, I only work with synthesis and chemical modification of guitar. However, guitar is also used in electrochemistry. There are 4 properties that distinguish guitar from other materials contain sp2 carbons. I won't discuss about this, however, I recommend this article for details information about electrochemistry use. The materials obtained by the synthesis described here has similar properties to guitar. Therefore, this material was called guitar. This is a flow chart of the equipment I used for guitar synthesis. Chemical vapor deposition was used here. We use it to 3 types of supports, carbon black, smaller silica, and larger silica. And vegetable oils was used for the synthesis, and a nitrogen atmosphere was used too. This is a short video of the equipment working. The time for the synthesis was 1 hour. Well, all guitar samples were sulfonated. The procedure was repeat 3 times for each samples. Solids were regenerated and after use in the esterification reaction. And the name of the solids after sulfonation can be seen in the projection. The reactor used in the experiments does not allow agitation. Pressure inside the reaction vessel was calculated using Antoine equation. The GCMS was used to analyze the products of the reaction. The table shows the results obtained in the esterification reactions of lauric acid with methanol without catalysis. All the experiments were done in duplicate. The error shows to a standard deviation calculation. After the first cycle of use, the catalysts were recovered, regenerated, and reused in the second cycle. Thus, the experiments corresponding to the second use of the catalysis were not carried out in duplicate. The last column shows the gain of conversion of lauric acid and the sulfonated guitar used on larger silica. These are the results obtained with guitar on carbon black. The results for the first cycle is statistically similar to the previous one. However, there was loss of activity on the second use. The reasons still need to be studied, but however, it may be related to lithium from guitar. The results for the first and second use are similar as with the use of larger silica. These preliminary results indicate that perhaps silica is better support choice than carbon black. In these experiments, we use guitar on larger silica, and the results shows that solid is active and ethyl esterification reactions as well. These results shows that the solid is active in esterification reaction of lauric acid with glycol. The table shows the amount of unreaction lauric acid, and this preliminary test shows the potential use of the catalyst. Guitar samples were characterized by XPX, XRD, and TGA. But I will not present the results because some data is not available yet. However, available data do not show change in the catalyst before and after use. Well, final considerations. All the solids shows achieved in lauric acid esterification. The results also showed that the solids can be reused. Therefore, they could be tested in alternative processes for the biodiesel production by acid catalysis. Preliminary results also showed that they can be used to produce acylglycerides. I thank to Armando McDonald and Francis Schenk for having me in Idaho, and also Farik and Jeremy for their collaboration. I thank University of Idaho, UFPR, and CAPS for scholarship. Thank you. Luis?
Thank you, Claudiney, for your presentation. Very interesting results. I am afraid that we already ran out of time, 10 minutes more or less. Maybe I'm here to be blamed because I did not control much of the time of our previous speakers, so we don't have much time for questioning. On the other hand, we don't have any question in our chat, so that makes my life a lot easier. I only ask our speakers whether there is any question you want to exchange among yourselves. You may use this the microphone if you wanted.
No, thanks from my side. I'm fine. Were very good presentations. Well, there should be some discussions on the catalyst, which is quite challenging. What about the preparation? What about the costs and so on? So that would be interesting for me. And the reuse. So there was only one or 2 times using the same catalyst. What about 5 times, 10 times, or did you check it, Mr. Cordeiro?
I only use the catalyst for 2 times. First use and regenerate the catalysis, and then second use. I don't use 3 times or 4 times, only 2 times. The catalyst is very cheap because it's produced from initially no, but now for chemical vapor deposition using vegetable oils. The cost of the catalyst is cheap, but the equipment for chemical vapor deposition is very expensive.
Okay.
Thank you very much.
Thank you.
Any more questions from our speakers?
I don't have questions, but I have a very brief comment on the talks that I saw. Very good, and thank you for that. In the case of Dr. Mittelbach, he got me thinking of hydrogenation of lipids and things like that. I shall study a little bit of that and then maybe drop him a line. In the case of Rafal, it was a very good presentation. We are aware of his work because he's been here also on print. Luis, you brought him. And I especially liked one slide that shows CO2 emissions and then the energy consumption in terms of autonomy of transportation, I guess, something like that. It's a very nice thing because it shows batteries. That's of course a very cheap technology inside the city, but when you see the overall cost and LCNS, it's complicated. And in the case of Professor Vargas, I'm quite aware of his effort, and it's very nice to see that that integrated system working and growing. And congratulations on that. And that's it. In the terms of catalysis, Professor Cordeiro, I don't work that much on chemistry of oils, but thank you too.
Thank you, Julio, for your words. Yes, the idea was to provide a 50-50 kind of division in the time between people from abroad and people from our institution. I think we succeeded in that regard, exposing a bit of the results that we are obtaining from the CAPESprint project. Since most of our speakers are related to that program, they're working together with some internationals to develop studies in both clean energy and biofuels. We heard that yesterday in the first session shared by Lucimara Roman, and today, in this session. So I thank you all very much for your effort in bringing all this information together. I'm really sorry that we could not have more people in the audience, but the beauty about the virtual world is that things will be available, for others to see in the future. So I agree with you, Julio. You made a comment about the extent of dissemination of this conference. I think that we failed a little bit in that regard. Even within UFPR, we did not see much dissemination of information regarding the conference. And that is probably one of the reasons why we don't have much more people involved. On top of that, it's the end of the semester. So a lot of people worried about classes and exams and everything. So hopefully they will have time afterwards to watch these presentations using YouTube or whatever other means that the university might offer, for people who could not join us during the meeting. So thank you all very much. Thank you very much, Martin, for your time and for your competence in bringing all that information together. Thank you also, Claudiney, Vargas, and Julio, should say. Oh, what am I doing with your name here? And I'd like also to thank Lucimara Roman for sharing the yesterday's session. She should be co-sharing this session as well, but she was busy with some other stuff. She's involved with the CNPq board and physics. They're busy analyzing all the applications they received, for funding. So thank you all very much. I think that we could then wrap up this session, and I'll give you a round of applause, virtual, for what you've given us today. And, Martin, please keep in touch.
Thank you very much.
Thank you very much
Congrats.
for organizing, and it was nice to join you.
Congratulations to everybody on the nice pieces of work that we have seen today.
Right. Thank you all. Have a good lunch, and see you another time. Take care.
Thank you very much.
Thank you all. Bye-bye.
Thank you.
We
Bye-bye.
will
See you.
Go for dinner now. No lunch.
Bye.